Hello there, and in this video we're going to do another example on how to test the difference between two population means. But this time we're going to use a different test, and I'll explain to you what that is and how it differentiates from the one before. So let us assume you have the choice to only go to one out of two movies, and you survey your friends on their opinion on a continuous scale from 0 to 10. So you ask a set of people about their opinion on movie A, and you get 8.7, 7.8, 7.3, 7.4, 7.7, and so on. And you ask people about movie B, and you get particular scores 6.5, 6.1, 5.6, 7.6, 5.9, 6.4, and 7.5. So if there is significant difference between the movie's perception on the general public, so that you can pretty much either randomly select one, and you pretty much expect your interest to be about the same, or should you actually listen or go to a particular movie based on your friends' opinion. So we can use like an average score for both of these movies and use that as an estimate to sort of determine which one is the best. All right, so let's go through the process for this type of hypothesis test. So we're going to use the mean to characterize which one is better. So the null hypothesis is that mu A does not equal or does equal mu B. So if that is true, then that means there's no significant difference between the two. And for the alternative, we're going to use the two-sided complementary alternative, namely mu A does not equal to mu B. And we're going to define mu D to be equal to mu A minus mu B. So from this definition, we're going to get the equivalent null and alternative hypothesis. Mu D equals 0 and mu D does not equal to 0. Okay, so from these two samples, you can calculate a bunch of statistics based upon that. So if you want to take the time to sort of do that, then I definitely recommend it if you want to work along. Or you can trust my calculations and sort of follow along. The keyboard doesn't want to go away. All right, so what do we have? So we can calculate, for example, the size of the number of people we calculated in A. So from here we have 2, 4, 6, and 8. So we have 8 people there. And in B we surveyed 7 people. So from these sizes, so this is going to be NA and NB. So that means the degrees of freedom for A is going to be equal to 7, and the degrees of freedom for B is going to be equal to 6. All right, so then we can calculate the sample means for each of them. So X bar A and X bar B. So if you calculate the average of each of these, you're going to get 7.71 and 6.514. And then you can calculate the variances. So S squared A and SB squared. So they're going to be equal to 0.244 and 0.591. And from these two averages, you can calculate X bar D to be equal to X bar A minus X bar B to be equal to 1.198. So this is going to be the point estimate for mu D. All right, so for the sake of this example, there it is again. So let us assume that sigma A squared is equal to sigma B squared, or perform F-test to check. But for the sake of this example, let us assume that the variances of these populations are about the same. So if we make this assumption, then we can use what we call a pooled variance t-test. Now, why do we use a pooled variance t-test instead of a paired difference t-test? Well, if we sort of go back to our movie samples, these values doesn't really correspond to one another. That is, these aren't the same exact people who went to the same exact movies. They're just randomly selected friends that have watched movie A and movie B. So that's why we use a pooled variance t-test instead of a paired difference t-test, for the critical reason that the variances are assumed to be true. All right, so since we're going to use a pooled variance t-test, we're going to calculate the pooled variance for our sample. So recall this is equal to the degrees of freedom for A times the variance of A plus the degrees of freedom for B times the variance of sample B, divided by the degrees of freedom for the entire hypothesis test. In this case, that's going to be nu1 plus nu2, or you may be familiar with the formula nu a plus nu b, nb plus na minus 2. This is the same exact formula, just rewritten in different contexts. All right, so based upon the things that we've calculated so far, nu a is going to be equal to 7. The variance of a is going to be equal to 0.244, plus the degrees of freedom for sample b is going to be 6 times its variance, 0.591, divided by the degrees of freedom for the entire thing, which is going to be 7 plus 6. And once we calculate that out, that's going to be approximately equal to 0.404. So that's the pooled variance. So if that is true, then that means the pooled standard deviation is going to be equal to the square root of the pooled variance, or the square root of 0.404, which is approximately equal to 0.636. All right, great. So let us assume that we have already chosen our level of confidence to be equal to 0.95, forcing an alpha value of 0.05. So if this is the case, then we can calculate our critical value, T alpha over 2, to be equal to T.IMV of 1 plus 0.95 divided by 2, comma the degrees of freedom for the hypothesis test, which in this case is 13. So once you calculate this in Excel, you'll see that this critical value is about equal to 2.160. All right, great. So from here, we can calculate the marginal error for the confidence interval. And this is going to be for the pooled variance t-test. So this is generally equal to T alpha over 2 times the pooled standard deviation times the square root of 1 over n1 plus 1 over n2. And just as a side note, you may see this sometimes written as, this keyboard. Sometimes this is written as T alpha over 2 times the square root of sp squared over n1 or na. This is going to be b and this is going to be a, of course, plus the pooled variance over the size of sample b. They're the same exact thing, except sp is factored out of this expression. All right, great. So our critical value came out to, what was that? 2.160 times the pooled standard deviation of 0.636 times the square root of 1 over the size of sample A, which was 8, plus the size of sample B, which was 7. So once you calculate this all out and make sure you want to put parentheses around those two fractions when you sum them, you should get a marginal error of approximately 0.711. All right, wonderful. So from here, what do we do? So our confidence interval for the mean difference, and we're using a 95% confidence level. So we're using x bar d as the point estimate for mu d. So that's going to be the center of our confidence interval, minus our marginal error for our pooled variance t-test. All right, so our point estimate, recall, was 1.198. Subtract our marginal error, 0.711, and then our point estimate, 1.198, plus our marginal error, 0.711. And once you calculate those boundaries out, you're going to get 0.487 and 1.909. And this is the confidence interval for our mu difference under a level of 95% confidence. All right, so once we have this, then we can start working on our hypothesis test, right? So our null hypothesis was that mu d was equal to 0. Notice that 0 does not lie within our confidence interval. It actually lies a little bit to the left, right? So since the null hypothesis 0 does not lie within our confidence interval, that is, 0 is not in between 0.487 and 1.909, that implies that our sample does not agree with the null hypothesis. Therefore, we're going to fail to reject the null hypothesis that the difference between them is 0. Or we fail to reject the null hypothesis that mu A is the same as mu B. They're the same exact thing. So that means our sample provides evidence to support the claim that mu A does not equal to mu B, which implies that one mu B has a significantly better rating in the population of movie watchers. And that's assuming that these samples were collected, they're all random, they're all independent, they're all unbiased, and so on. So which movie is better than the other? Well, we can claim that movie A is better than movie B. Maybe we want to go that far, say movie A is better than movie B. Why are we saying that claim? Well, recall that the sample mean for movie A was 7.71 and the sample of movie B was 6.514. So our hypothesis test pretty much says that 7.71 is significantly more greater than 6.514. And if you're familiar with movies, maybe you might disagree with this assumption, but at least based on our sample, this is true based on our hypothesis test under a level of confidence. And that's pretty much how you conduct a pooled variance t-test. And here, keep in mind, the only reason we were able to use a pooled difference t-test was that these samples are independent from one another, and we assume that the variances of these populations were equal. If you break one of these two assumptions, then that means you have to use, so if you break the independent case, that means you have to use a pair difference t-test. And if you break the second assumption that the variances are equal, which we sometimes call a homoscedastic population, then that means you have to use what we call a Welch's t-test, which is going to be the subject of the next video example.